Simple adaptive system, module SA. This is an adaptive filtering situation which has a lot of the basic concepts of adaptive filtering, but there are no matrices, there's no vectors, there's just scalars. There are, however, many assumptions made here about the random processes involved. These are wide-sense stationary random processes. This is the situation. There's a transmitter, a channel, a receiver. Typically the transmitter is fixed, some coefficient A. The channel is fixed, B. There's noise added in the channel. The receiver is here, an automatic gain control. Wn is the coefficient that needs to be updated. Dn is the estimate of the signal D, and E is the error. D is here at the transmitter and the receiver. The D here would be programmed into the receiver. It would be used during training. It could be programmed in at the factory, and so this is training using correct decisions. And conceptually, the idea might be here after training that the value of W becomes 1 over AB, so that AB times 1 over AB means that the estimate of the desired signal is approximately close to what was sent, meaning the error is approximately 0. But the adaptation is in a minimum mean squared error sense. Now these are random processes. Dn is a random process, this data, +1, -1 over all time. Eta n is the noise, it's a random process. So for example, with this random process for D, the mean value of D is 0. And this capital E is mathematical expectation taken over the ensemble of the random processes. And because it doesn't matter what value of n we choose, D, D1, D3, the mean value is always 0, meaning the mean is invariant to the time at which we take it. It's invariant to a time shift, which is something you get in wide-sense stationary random processes. The expected value of dn dm is 1, 0 for n equals m, n not equal m, and it wouldn't matter about the time shift again, meaning the expected value of d10, d11 would be 0 because n is not equal to m. The expected value of d100, d101 would also be 0 because it's invariant to the time shift. So the mean value of the random process is 0. It's uncorrelated, meaning if n is not equal m, it's 0. And because the mean value is 0, this is actually the variance at any particular time. And the data can either be -1 or +1 with equal probability in this example, which makes it just about as easy as you can to manage. dn hat is the estimate of the desired signal. It's Wn times BADN plus Wn times eta n. So dn, and this is the diagram here, dn is the desired signal, dn hat is the estimate of the desired signal. It will always be of the form actual minus estimate, at least in this presentation. Time starts at n equals 0. The initial coefficient for W is 0. Eta n is a random process. The mean value of the random process is 0. The variance is sigma n. It's uncorrelated, and the data and noise are uncorrelated with each other. The error is the actual minus the estimate. You're going to have to look at this. This is a very high-speed summary. You could bring many questions to me afterwards. So that's the introduction and the setup, but I'm going to go through very quickly at this point. From this point on for the next 10 pages, and you'll have to study this material and bring questions to me then. So the problem is that the receiver must adapt itself to make dn as close as possible to d in a minimum mean squared error sense, and this is the performance criterion. The mean squared error is a function of Wn, and this is the mathematical expectation, so it's the mean of the square of the error. The expectation is taken over the ensemble of the data and the noise. This performance criterion will be used often throughout this course and these lectures. There are 3 reasons for its popularity. It makes possible the mathematical analysis of the systems, which I'll do over these next 10 pages. It's used in simple adaptive systems, and it upper bounds often the probability of error. As shown, it is a function of Wn here. It's a function of Wn. You choose a Wn and then find the mean squared error. These are some calculations. You could just do this calculation. R is the mean of Rn squared. You put in Rn, square it, expand it. The mathematical expectation of the sum is the sum of the mathematical expectations. Work out the mathematical expectations as what's given. Do the same for P. This R is the mathematical expectation of Rn squared, and turns out R is actually the autocorrelation. P is the mathematical expectation of Rn with D, and that's the cross correlation. This is also sometimes called, in the class of adaptive filtering, it's an inverse filtering problem. It's also called an equalization. It's also called a joint process estimator. At this point, these are just calculations. I've given you a sense of R and P are actually autocorrelation, cross correlation. Page essay 4. The mean squared error is the mean of the square of the error, and if we put in the, En is dn minus dn hat, and so on, we get 9 terms. Work out the expectations, we get this. Going from this line to this line, I've just completed the square. It's just an algebraic property. And so an, bn, and sigma n squared are fixed parameters in this situation. Here, the mean squared error is a quadratic function of Wn. And the value of Wn, which makes this mean squared error smallest, is when Wn equals what's here on the right, so what's squared is 0, and what's left is the minimum mean squared error. And it is a quadratic function of the tap weight. Page essay 5. So the value of the mean squared error, which causes the mean squared error to be a minimum, is AB over A squared B squared plus sigma n squared. If I scroll over to here, in that expression, when Wn is this, what's in the argument becomes 0, and you get the minimum. So that's the minimum mean square. That's the value of W, which minimizes the mean squared error. And note as sigma n approaches 0, this approaches 1 over AB, as I indicated earlier. The minimum mean squared error is actually just this term here on the right. And again, as the channel noise approaches 0, then this approaches 1 minus 1, or the minimum mean squared error approaches 0. So observe the minimum mean squared error is between 0 and 1. Here, it's between 0 and 1. If it's 0, you get perfectly good performance. In this case, it's the worst performance. The worst you could do in this situation is if you just set W to 0. If you set W to 0, the estimate's always 0, and the error is just taken from the data, and that's the performance of 1. The solution of the minimum mean squared error problem is just if we look at that expression that was found here and we just rearrange it, we can rearrange it like this, and this is RW equals P. These are called the normal equations. The autocorrelation times the minimum mean squared error solution is equal to the cross correlation. If you know R and P, then you can find MMSE as R inverse P. In practice, the normal equations are a set of linear equations. To avoid solving them explicitly, simple adaptive schemes are used. Two of many schemes are the steepest descent and the stochastic gradient. The stochastic gradient is also called the LMS, or least mean square algorithm. And so the mean squared error is a quadratic function of W. That was shown here in this quadratic expression. That's the mean squared error. So the mean squared error is a quadratic expression of W. That's the minimum, the W which gives the minimum, and that's the minimum value. And so this is the desired endpoint. And initially W might start at 0, but we want to update W in the adaptive filter here. Initially, the weight here starts at 0, and we want to update it over time to find the minimum. So the steepest descent algorithm is shown here. If we look at the minimum mean squared error expression, or the function here, this is the minimum mean squared error, and if we take the gradient of the minimum mean squared error, we get this line. And the idea is that you update this iteratively to start from a Wn plus 1 is taken from Wn according to minus mu over times the gradient of the mean squared error with respect to w. Mu is the adaptation constant, and it's chosen to be sufficiently small to achieve convergence. And if mu is small enough, the algorithm will iterate towards MMSE, getting closer with each iteration. However, in practice, the mean is difficult to calculate, and instead of the mean gradient, the instantaneous gradient is used. So this is the steepest descent algorithm. The stochastic gradient, or instantaneous gradient, the idea was to just drop the e, because it's too hard to work with, so let's drop the e and see what happens. This is a creative leap. Bernard Widrow at Stanford found this in the 60s. If you get a creative leap correct, then you get known for it. And in fact, Bernard Widrow was correct, but it took 30 years to prove that this is convergent, that it's a stable algorithm. And if we evaluate the gradient of the square of the error, it's shown here, and this ends up creating the LMS algorithm for this automatic gain control system. W starts at 0, and then at each iteration, one increments W. Page Essay 10, switching from training to known data. So if the data, this is that diagram shown earlier, up here at the beginning on page SA1, really is shown here. And we were training it using actual correct decisions, but after training, one often switches from training to operating on local decisions. And if most of the local decisions are correct, it's effectively the same algorithm. If you're at the global minimum and most of the local decisions are generally correct, you will stay at the global minimum. So you train into the global minimum, then you switch to operate and likely stay in the global minimum and avoid local minima. The training sequence, which is programmed into the transmitter and receiver, allows you to do that, programmed at the factory. This training sequence may be part of a standard as well. So during training, the minimum mean squared error surface might look like this, but during operating, it becomes a complicated surface, and hopefully once you train to the global minimum, you stay at the global minimum instead of getting out of the global minimum and falling into a local minimum. There is some code here which implements the simple adaptive system here. And this is a result of training running this code. After convergence, in this particular example, if we look at the code, I'll scroll this way so I don't jump around too much. If we look at the code, the value of A and B were 10 and 10. So after convergence, the value of W would be 1 over 100. But in fact, this is the magnitude of W squared, so it's 1 over 10,000. After convergence, this is the value. This is 20 log n base 10 of the magnitude of the error versus time n. And over time, it converges. This is a typical shape of a learning curve. This is called the learning curve, where it iterates towards the global minimum, and then it achieves the minimum here. And you can see the evolution of the coefficients W versus time as they get closer and closer to the global minimum. And in fact, there might be a scaling error here. Let's see. The variance of the noise is 10 to the minus 1. I might have a scaling error here in that the minimum mean squared error after convergence looks like it's around minus 50, minus 60 dB. But, oh no, that could be right, because the signal has a power of A is 10, so the signal power is probably A squared, which is about 100, and then with this small variance of 0.1, this is the minimum mean squared error after convergence, around minus 50 to minus 60 dB. Okay, that is the simple adaptive system. I will continue now with the simple adaptive system complex. That previous example, the coefficients were all real. Here it's complex, and this adds an additional level of complexity to the situation because basically in the because of the gradient, you and complex numbers, in plain language terms, you can, if z is a complex number, dz, if it's analytic, the dz is 1. But dz conjugate dz, you can't take a derivative of a complex conjugate, because for an analytic function, it's got to be the same value no matter which direction in the complex plane you approach the point at which you're taking the derivative. And so even though we don't have vectors and matrices, when you add complex numbers, it makes it a little more complicated. And so this is simple adaptive system complex. If a and b are complex numbers and dn is a complex random process that has a variance dn, if sigma d squared is 1, it might be because the real and imaginary parts of d each have a variance of a half, so that the sum of the variances, so the real and imaginary part contribute to this variance. This is the variance of the noise, and it's complex, so you have a conjugate as well. Now, there are two ways to represent the numbers. Again, the error is the actual minus the estimate. The error is a complex number. W could be the coefficients that our what are the coefficients in the adaptive filter? In the simple adaptive system, the coefficient was W. And it just mathematically, it's actually easier to work with W and take the conjugate and then multiply by the conjugate to get the system. Now, if you were to build it, you wouldn't just put a conjugate, you just put a coefficient here that's complex, that's adapted. But mathematically, it's easier to be consistent with some other definitions to use W, and you conjugate W to create V, and then you do a multiplication of two complex numbers. Consequently, dn hat is dn BAD plus Vn eta n if you're using eta, but since V is W conjugate, if you replaced V by W conjugate, you would have this expression. The data has real and imaginary parts. The complex coefficient has real and imaginary parts. If you take the this is not the steepest descent, it's the LMS. If you take the gradient with respect to W, you have to have a real part and an imaginary part. There are various ways to represent this, but if you use gradient, you'd have to have a real part and an imaginary part. And if you evaluate the mean square, the square of the error, like this, and then take the gradient with respect to the real part, and then take the gradient of that with respect to the imaginary part, you get these two. This should be the LMS update, would be the following, if you work it out all the individual pieces. But you can combine those back together and make one update equation like the following, if you combine the real and imaginary parts and use complex again. Again, that shouldn't be steepest descent, it should be LMS. Then, continuing with the algebra, you get the following. And so this is an easier to work with mathematical form of the LMS for complex numbers. If you were to use V, where you replace W by V and then conjugate everything, you would get the following expression. So it depends where you put the conjugate, depending on your implementation. This one with the W's is mathematically easier, but using complex numbers, which is relevant in some adaptive filtering situations. If you're working in digital communication systems and you have in-phase and quadrature components, then you have complex numbers that you have to work with. This is a summary of the simple adaptive system and what happens when you have complex numbers in the simple adaptive system. Thank you.